things are everywhere. Hotels, restaurants, random food products, your grandma's forehead, literally everywhere. And you're about to help me build one, because if I just tell you, you'll forget in like 5 minutes. First, let's pick a size. Anywhere from teeny tiny to no. That will do. This grid is 29 by 29 pixels, so this is a version 3 QR code. It also needs a white border called the quiet zone. This exists because QR codes are already pretty chaotic and scanners don't want to deal with a messy background on top. Now, in these 3 corners, we'll draw a few squares. These are called finder patterns, and they help to orientate the code, because the bottom right corner should never have one. Also, scanners are dumb, so we add a few spaces. And now we run into our next problem. If we view the code at an angle, it becomes distorted. Since we're trying to read patterns and these two aren't the same, distortion is bad. So we add this 4th square called an alignment pattern. You can see it here. The scanner measures the distance from this alignment pattern to the finder patterns to correct the distortion. The bigger the QR code, the more alignment patterns it has. Our code just needs one though. Alright, next up is this single black pixel. It doesn't do anything, it just exists. And that leaves just one more fixed part, the timing strips, which are alternating black and white pixels that tell the scanner where the grid is. There's also these format strips, one in the top left here, and one split between the bottom left and top right. But we'll come back to these. For now, let's add our data. We'll start here and fill in a 2-wide zigzag pattern. Each pixel represents a single bit, white for 0, black for 1. The first 4 bits represent the type of data, Japanese kanji, binary, alphanumeric, or numeric. To choose the right type of data, let's decide our message first. We'll use the link to my channel. This is easiest to encode in binary, so we'll use exactly that. The next 8 bits, or 1 byte, show the length of our message. In our case, it's 40 characters, so we'll add the binary for 40. And now we can start spelling out our message. H converts to this, and so on. After HTT and part of P, we reach this format strip. So we just move along and continue filling in our characters. If we reach a fixed area, we just skip it and move on, until all of our message is filled. 4 white bits are then added to signal the end of the message. Now, if you have a functional pair of eyeballs, you'll see a big gaping hole. So what's it for? Error correction. You see, QR codes can still be read with up to 30% of the code literally missing. Here's how it works. Let's start by finally looking at these format strips. The first 2 bits show the level of error correction. Low, which can recover up to 7% of the code, medium, which can recover 15%, quartile, 25%, or high for that full 30%. The next 3 bits indicate the mask, which comes last, and the other 10 bits simply correct the first 5. In fact, they're so important that this other strip is just a copy. To demonstrate, let's imagine we only have 2 possible combinations, 00000 or 11111. If the scanner reads 00010, it was probably supposed to be 00000. The difference is, these first 5 bits don't have 2 possible outcomes, they have 32, but the principle is the same. This works fine, but the only problem is that we're using 10 bits to check 5. That's not very efficient, so we need something smaller for the actual code. We'll use something called Reed-Solomon error correction instead. Pick 3 numbers, 7, 3, and 13. I could send you these numbers, but then you'd have no clue if something went wrong. So what do? Well, I hope you remember algebra, because I want you to treat those 3 numbers as the first 3 coefficients of a quartic. Don't worry, I won't make you do any maths. Now, I'll add 2 extra numbers so that this quartic is divisible by both x-1 and x-2 with no remainder. Those numbers are negative 165 and 142. Now, I'll send you all 5 numbers, and you can plug in x equals 1 and x equals 2, and both should give you 0. If they do, that's it, the numbers are correct. But let's say the 3 swaps to a 4. Now if you do the same thing, they don't equal 0, so there's been a mistake. We can find the mistake by swapping each coefficient one at a time for a variable, and solving it using x equals 1 and x equals 2. As you can see, we find that for the first number, the solutions are different, so this number is correct. But for the second number, the solutions are the same, and they equal the original number. Not only did we find the error, we corrected it. Now, we'll fill in this space with a bunch of these extra numbers. And this is just dead space, so fill it however you want. But it's still not ready. See this? How big is that patch? It's hard to tell. To fix this, we use a mask, which inverts some of the pixels. The format strip tells us which one to use. And in this case, we'll flip pixels in every 3rd column. And that's it. We've built a working QR code. Go on, scan it. Even cover some of it if you want. And maybe subscribe while you're there, because that took way too long.